Hello, everybody, and welcome to a new final project presentation ceremony from our masterclass. Today we have one presentation from our student Kailash Khadka. His project is titled Warehouse Automation Using Laser Perception. So he's going to be showing us in a moment his project and doing also a live demonstration connecting to our real robot here in Barcelona. So yeah, without further ado, I think we can say hello to Kailash so that he can introduce us his project by himself. So hello Kailash, if you can share for a second your camera so that we can see you.
Yeah, I'm already live. I'm sharing it. Hello, Alberto again.
Yeah, we can see right now your screen only.
Oh, my screen only?
Yeah. So you can
So
just
my
stop.
video, yeah, okay.
Yeah.
I
You
can
can
start
just
now?
stop sharing your screen and so that you
Oh,
can
I see.
quickly. Okay, there we go. Now we can see you. Yeah.
Okay. So hi, yeah. So can I start? So my name is Kailash Khadka. So thank you for having me here today, Alberto, for this my final project presentation in this my project. So what I'm trying to do is, so we have a warehouse automation setup. So I want to so so program the warehouse robot, which is RV1 robot, such the way that it can detect the self in the warehouse environment, and it can dock to the self and bring it to desired shipping location. So everything is implemented, and we'll see a demo shortly. So yeah, so can I start my presentation now?
Yes. Go ahead. Let's just start with the technical part.
Okay, let's see. Now I'll be sharing my screen. Can you see the screen right now? The presentation.
Yes, we can see it.
Okay, so yes, again, so my project is titled Warehouse Automation with LiDAR Perception. It is in partial fulfillment of my Robotics Developer Masterclass. So let's begin. So we already know that robot is already widespread use, and with the rise of e-commerce, so it has even more grown, and the demands of the 24/7 logistic has even boomed it. So we know that human workers can not only meet the requirements, so robots are here to hear human. So with the robots, we achieve automation, and which means our businesses are scalable with high precision, and it also brings the cost effectiveness. So few stats here. There were already 750 thousands of robot in Amazon warehouse already in 2023, and it is expected to even rise from where it began in 2013. So it was around 10K. So we can already see a huge jump here. And according to the global market insight, so the current market value as of 2024 for the warehouse automation robots only is $14.7 billion, and it is expected to go to grow almost tenfolds to 117.3 billion in 2023, with the growth rate of about 23% cumulative average. And then, so according to Gartner, 85% of logistics will be fully automated by 2030 already. So we can safely say that robots are not things of future; they are already happening right now in our present. Okay, so for this project, the main objective of this project is to design a fully autonomous robotic system so that the robot can navigate the warehouse autonomously. It can detect the self card anywhere within the warehouse environment, and dock and lift the self, and then return the self to its origin location, or any location requested. And also this whole everything should be controllable and can be monitored by web UI. and also the whole thing should be controllable by the workflow should be controlled by using this machine. So these are the project objectives, and so in order to achieve my various objectives, so one of the objective is to do the navigation setup, so we need to do that. And for that we have the first thing is mapping and localization. So I use the cartographer node, the package from the nav2 stack for the map making using SLAM, and also it uses AMCL for the localization process, and also the global localization service is carried out using the AMCL's. We have one service, so which is a reinitialize global service. We can use that for the global localization service. And next is path planning and execution. So again, nav2 setup is used. The application stack is used for path planning and execution. So high level path planning uses global cost maps, and the low level of execution uses the local cost maps. So by default, the all the default path planner is used, and also the default DWB controller is used. And in the recovery behaviors, we have spin backup. And so cost map also uses various layers like static layer, obstacle layer, and inflation layer. The next is so once the navigation stack is ready, it is communicated with or by the commander API, which gives us Pythonic way, or maybe using C++ also in that matter regard. So we can send high level of goals to the navigation stack using this API, and it has been used in this project to follow the weapons for the self search. And once the self is docked, searched and docked, so it is also used to deliver the self to the shipping positions. We can also send cancel and resend goals whenever needed. And the source logic, it follows the robot follows the predefined source route, which is a list of dynamic waypoints. And once the robot figures out where the cart is, so the reactive behavior starts by ending the current search. Next thing is self-detection. So laser scan, the data from the laser scan is used to detect the self. So that is the only perception available, no vision. And so we get the range and intensity values from the sensor, which is used the intensity of the reflectors in the cell's legs are used to locate and locate this card, and then also that information is used to dock. And I also have used filtering techniques to remove the occluded points, which is also often referred to as shadow points. And the filtering technique, it removes the misleading data points caused by the occlusions or sensor artifacts. And we could and for the docking behavior, so I have used this aligning technique using the ROS2 transforms. So it uses 3-point technique, where there is like approach point, and there is the edge of the card and the center point. So it follows that in order, so that the docking behavior is works as expected, goes inside without any collision to dock the self securely. And once the docking behavior is completed, so it also updates its footprint. uh, Yes, so the robot size is changed whenever we dock into the cart, because whole system is now, it acts as one, and then the robot movement is also need to accommodate the size of the carts. So that's why we need this footprint update when it is docked, and also when it is when the self is released, we need to change back to the robot only footprint again. This is, let me explain how the robot docking works. So first of all, we have our, this is a card somewhere in the robot. So once it is detected where it is by the in the source step, so the next step is docking. So for example, if we have our robot here and the card is detected based on the laser points that by reflecting. So there are the reflectors, as I mentioned before. So these reflectors, they give the laser signals, and that is sensed by the lidar. And then once those signals are detected with confidence, so we have two leg points and we calculate a midpoint in here, and that is where is referred to as card frame. And once we have that card frame, so based I draw a perpendicular line here through the edges, through this line, and then uh, s- okay, so and this perpendicular bisector within certain distance, so there is also approach frame is created, so that first we can get to the approach frame and then align it towards the center of the card, so that the precision is better. And once we have that, so the robot first aligns its yaw to this approach frame, and once the approach the yaw is aligned, now it moves toward that approach frame uh, in steps. And so once it is robot reaches the approach frame, it again the aligns its yaw to match to the card frame to face towards the card. And once it is also matched, so it is matched, so it now moves towards the card frame. And and once it reaches the card frame, it should go inside to the center of the card, which is half card width. Uh, and once it is reached this position, so it lifts its elevator to dock. So, and then as I mentioned earlier, so now the robot's whole effective size has grown, which should be reflected by updating both global and local footprint to the dimensions of card. Yes, and so regarding the
Hello,
design,
Kailash.
as
Can you hear me?
yes, please. Yeah.
Yeah, yeah, no, just a quick reminder to check your project, okay, so that you don't get kicked from it, okay.
Okay.
So with
Uh,
the timeout uh, that we
okay.
have,
Yeah.
you know.
Give me a second. I will quickly check it. Hmm. Can you see my?
Yes,
Okay.
yes, yes. We have it. We have it there. Okay, okay,
Yeah.
okay,
So
okay. Yeah,
38
yeah.
minutes.
Yeah, yeah, just wanted to make sure that the inactivity detector was not going to kick in. And also
Okay.
just
Okay.
a quick reminder while everyone is following your presentation that if you have any questions for Kailash regarding his project, you can leave them here in the chat, and I will try to pass them to him for answering later. All right. So yeah, sorry for the interruption, and you can continue,
No
Kailash.
problem. Okay. So let me restart. Um, so where was I? Yeah. Um, so yeah, I just completed the how the approach works and how approach and docking works.
Wait,
So now
Kailash,
I
we are
yeah.
seeing now this audience window. So I think you have to click on enter full screen mode or something.
Oh, okay.
Yeah, there. Okay, yeah.
Okay.
Now it's
Now
good.
everything good?
Yeah, yeah, yeah.
Okay. So this is so now let me explain how my whole this system has been designed. So four major components: web page for interactivity monitoring, and the warehouse manager, which is the state machine that orchestrates the whole steps and manages failure. And there are other ROS2 overlay contains all the nodes, including the warehouse manager itself. So there are like different nodes like localization load, the attached load, the detection, sorry, not load, attached node, detection node. And I would also like to, so I have used the ROS to humble as which is in the ROSIC as the underlay, which is also like it does the most heaviest part, of course. So that's why it is worth mentioning here. And so for web page UI, so I've used the Vue.js for the reactive UI components in the front end, and for ROS integration, ROS libjs is used for the bridge communication, communication to the all the ROS nodes. And EaselJS and ROS2D.js is used for canvas rendering and 2D map visualization. So next is the protocol used is WebSocket, which is taken care of by the ROS bridge for the communication of real-time data. Um, and so web page UI has the robot control mechanisms, which change the command velocities by publishing the control velocities. So there is joystick interface and also directional movement buttons. So these send the command vels. And for the warehouse automation monitoring, so we have the elements that it actively monitors the state machine by this status. It displays this various status in the UI, and it also have the buttons to trigger the various tasks like localization, cart, source, attachment, and etc. It is a multi-step control process. Um, so for the visualizations, we have there is a 2D map viewer which detects the robot, detects and follows, not detects, it is actually monitors the robot current robot and cart position. It tracks, and there are also shipping point markers. And so as I mentioned earlier, for monitoring, there are like status indicators which state the which helps us to monitor the state transition using visual feedbacks, and there are also failure counters. So this is a high level of web page, the design architecture. So web page has various buttons and displays for monitoring and control of the state machines. So ROS2 overlay has the state machines, which goes through these steps one by one in order. As long as they are successful, the previous one is successful, and there's like other fail safe and go back mechanisms, which I will discuss in next slide. And also the ROS overlay contains measured nodes like approach service server, which is responsible for um, attaching the for docking, I would say. And there is also self-detector node, and the other's importance is the global localization action server. And the Wave UI also can control the elevator up and down functions to independently lift the I would say manually. So it obtains that by directly communicating with these topics. Next, all these the wave interface is a little bit less heavy, so that all the heavier task is done in uh, the in the state machine node. So all the task is done in this person. So the wave interface, they all the features, it uses the topics, and these buttons, they send the trigger signals by publishing to the topics, and the incoming system status comes through the topic as well, and it parses and displays the system status in its interface. So we have our enable feature, which enables the whole system by clicking this button, and it sends the trigger, and then it starts the state, first state, which is the start state. And the localize button, it sends trigger to the globalize, and the sends trigger through the topic, and the localized callback is triggered then, and it starts the localization, which sends then this sends the action call to the global localization server and waits for its feedback and the result. Once it is completed, so it is ready to go to this state source. So if in manual, so we have to send the signals step by step, so that one after another this task can be achieved. And we also have the auto start button, which triggered which when triggered, it uh, runs the whole these steps automatically, so that it does localization, search, attach, and go to SIP, and even to return home automatically. So I have implemented this fall through the architecture, which if I request for attach state, for example, it automatically triggers the localize, search, and attach, so that these prerequisites steps are taken care of automatically, so that even in the manual, so if I trigger the this go to SIP, then it has been programmed to complete the previous steps. And when we send the auto start, so it actually triggers this final step, so that when it is triggered, so it begins from the start to finish automatically. So yeah, and so this state machine, it triggers in right time through this there are like two action server. So this commander API is used to communicate to the navigation stack. And so for the self-detection and approach service, we have service calls, and the self-detector also sends the uh, detection status to the calling state. And the elevators, they directly communicate with the robots elevator up down for manual elevator docking. So yeah, this is the detailed system status. Next is, so yeah, state machine. So I have implemented that in Python for keeping it simple and easy to test without repetitive compilation. And it has fall through approach implemented, so that previous steps as prerequisites should be completed first. And it is a modular and testable logic, and it also has logging and fallback transitions. The next is the main states are the initialize, localize, source, and detect and dock, and then it goes to navigating to the shipping location. And once it is there, so the next step is detach and return to home. So these are the many steps. And yeah, so for my project, so it is really a tough one. So there were a few challenges that I had to overcome. So nap 2, so there is there was 4 false obstacle detected, because the robot does not scan 360. It has the blind spot in the black side. That is the feature of the laser. So its range is does not cover the backside. So there are the trails left behind when the robot carries the self, and it thinks that because it was there's previously the position was occupied, so the that in the that is reflected in map as obstacle, which is definitely a false one. So hence it interferes the navigation. So I figured out that there is a clearing feature in the obstacle layer of the global cost map. So, and the next one is the navigation backup failed, maybe partly with the same reason, because it does not have the laser information coming from the back. So I had to implement a custom backup service, so that it does not care about the whatever being lack of the lasers sensor data. And also for localization, there were like two competing pose, because when in the localization steps, the particle filters those are scattered around, and they try to tend to it is especially the problem in the simulation, but in the real robot lab, because the surrounding the environment is not symmetric, so there's no such problem. And we can simply uh, avoid this by putting some extra objects in the environment, so that the environment is no more symmetric. And also there was one important this is the most challenging part. So there is like self when the detection node is working, so there is the extra I think reflectors from the charging station, which emits, so which also poses as a candidate leg. So I had to use the shadow filters and the cost based leg selection method, um, based on the the cost is based on the average intensity and the leg length. So which is the desired leg length is around 60 centimeters, and while the docking station is I think around 30-35 centimeters. So the cost based approach is used to select the right one. And for the precision and docking alignment is also a problem, and then I implemented the three-point technique that I described earlier, which is to go to approach and then card and then to the center in gradual steps, while maintaining the alignment in each step. And so for the waves, the raw sleeve is, I don't think it has a proper support for the action servers. So I simply decided to use all the topic based triggers, so that heavy lifting is always it is done in the ROS side, ROS nodes, and this also keeps design simple. Yes, now it is time for the live demonstration. So where we will see how level everything this task in action. So yes, so Alberto, I'm briefly halting my presentation, and I will be going through the project where I need to prepare. Can you see the screen though still?
Yes, we can see your project. Yes.
Okay, so let me connect, and okay, everything looks good. Okay, so this is our real-time environment. So I have to start a few things here. So, and for this demonstration, so that I can see the logs if in case anything goes wrong. So I will individually um, come say open the this different nodes in different uh, tabs. So this is the first one is localization server. So it uses the map, and in the next one I'll be triggering the path planner. So these are the navigation stacks, and it also open up the RVs for us. Let me also run the this next one is for attachment server. So we have the RVs and the map ready for us, and this is going to be attached. This is for the docking. Let me do it. Okay, I have a build command which should not take more because everything should be okay. Now we have attachment servers ready as well. The next would be localization, I think. Yes, it is localization in real environment. So I also have this positioning node for publishing the robot and card positions to the robot and card position to the web page. So this is for the web page. Next one is our main node, which is warehouse manager node. So it will be here. So it is also starting. The next one I need to run the web page. For me, I have chose to use the HTTP server that Python ships by default. And for that, I need web page address and ROS bridge address. So let me click this one and hopefully get something. Yes, we have that. And the ROS bridge address is 050, which is good. So let's connect. So we have the connection, and map serving is Mac server. Sorry, map is available. So these are the a few docking stations that I can trigger using this button. So let me quickly. So these are the control panel where there are like various buttons to send command wells, and command wells can also be sent using the joystick control. So these are auxiliary control where Alberto up down and the shipping. Can be triggered, and the main state control are here, so I can just send enable command, and then these are the status. So okay, let's look into where is that thing. Okay, I have in same same page, so I think I'll have to split. Um, okay, can I make it this? Okay, so I don't think I can make it any better by squeezing this. Okay, I think this is a little bit. Alberto, do you think this is good enough? Um,
I think
can you see it?
we can see, yes.
Yes. Okay. So I think this is
Okay.
the good view. So I have already enabled by sending start key. So first thing we can do localize. So I'll press the localize button, and so you can see here localization command has been sent and initiated. So that is also reflected as current state and localization in progress. It can also be visually figured out by this yellow blinking kind of localize button. So let us wait until this localization is completed. So it is still in progress.
So this is the global
It,
localization, right? That you were talking
yes,
earlier,
global.
Kailash?
Yes. It is globalization that. So we saw that particle. It was red at the very beginning because everything was the particle were scattered throughout the map. So now they have all converged to the real location. So it also uses the covariance that is provided by the AMCL post
Hmm.
for this detection. So once covariance is for X, Y, and Y is good enough, so the localization is complete. So that is what we can see. So it has localized. So as road is facing the upward, so it is also shown the same, and it can also seen from this 2D map. Okay, so now next step is sourcing for the card. So I will also trigger this manually for now. Okay, so the next step is sorting. So it first come now it will navigate through various waypoints that is predefined. So we can see the web is also tracking the robot movement and orientation. So the robot it moves through the various waypoints and does sensing the localization. Not localization. The um, the self detector is now in action in background, which is doing the search for us. So once it the search it finds the card, the search should abruptly end and then say that okay, search is complete by green signal here, or it can also we can see the card attachment is in progress. Okay, now I think it has detected, so which can be seen by the transform that we can see here. Oh no, what happened? So RVC is out. So we can see that source step has completed. It has already localized. So let me start attach server service so that it um, goes and docks. So once it goes into the center, so now it attaches. So we can see the lift is being the elevator is in action, and I think now it says that attachment is completed. So now next step would be go to shipping position. So I can just press the go to ship position. For that, we have to manually select one of the three positions, B, and I think we can
Kailash,
see
can you
it
hear
here.
me?
Yes.
Can
Yeah.
you try in the for RVs to minimize and reopen? No, I mean inside the window, not so the RV's
I
own
see.
window. Yeah,
You mean
there.
this?
If you minimize in the top blue bar from there and maximize again.
Oh, yeah.
There it is.
Nice,
Yeah.
nice. Okay, so we can see that I don't know. It is very faint for that matter. We can see that robot has the footprint has been updated to reflect that it has also docked. Now I can trigger the go to ship. So it is in action. So it backs up, it comes out of the location, the SIP, and now I think it is waiting for us to send select one of these uh, three shipping locations, which can be seen here in the message. So I don't know where I started that. Yes, so manually select a shipping port waiting. So it is waiting for us. So let's not make it wait anymore and select one of these. So I'll select this position here, which is A, B. Okay, now it is going to the location B. hmm So, oh, okay. So it is approaching the shipping location B. Now it will release and come out, and we can also see that footprint has updated back to the circular one to reflect the robot only. So now the go to ship position is also completed. Now I can simply press to return home where it all began. Okay. And now, so we have this cart here because the position is updated. Okay, what next? So now I can also demonstrate the auto start. So let me first let it complete the return to home. Okay. Okay, so the return home, one cycle, whole cycle has been completed manually. So let's do the same thing automatically. Let's try if it triggers. Oh, I don't see. Maybe I should. Oh, something hiccup. What happened? Skipping. I don't know. Some okay, let me quickly restart this thing rather than waiting. Okay, so let me. So I think when I start, so it should auto enable and kick in. Yes, so it is auto enabled system and start the from the localization. Mm, so localization should take maybe 15 seconds. So I think we can see the localization is completed. Now it should automatically transfer to the search. So it is moving through the prescribed waypoints. I mean predefined waypoints. So from these frames, we can see that it has already detected the card. So okay, now it is going to end the searching position and trigger the attach. So for that attach, it is trying to adjust to the approach so that the docking is a bit precise. So now once it is docked, okay, maybe the precision was not very good. So I could have pushed a little bit of. Okay, let's see what it does. So maybe it failed. I don't know because the okay go to ship is waiting for the manual pose. So maybe we can put somewhere here, which is position D. Let's see. Okay. Now, because it is not properly docked, I think it is struggling a little bit. It is not given up yet, though. So it is also approaching the docking location T. Okay, now it says so enough, and then it is going back to home position. So yeah, I think this is so we have completed 2 cycle. So anything from Alberto?
Hello.
Yep.
Okay, so can we, for example, try starting the robot somewhere else? Is it
Start.
able to handle that?
So wait, whenever sorry, I think this is automatic. So let me stop this because it is in auto mode now. It is doing that in loop. Uh, yeah. So coming back to your question, you want so if they yeah. So let me move to the robot to different position.
Hmm.
Let me connect this one. So the thing is that it always comes back to home position to begin the search. So because of the time constraint, I could not implement what I had the solution. So, um, but yes. So if I say maybe I'm just bringing manually,
Mhm.
I can also use manually to different location. So maybe forward here, right? Okay. So let me start from somewhere here, right, which
Mhm.
is away from the. And first thing we do the localization. Let's see how it works. So the localization is working. It is taking time. Yeah, localization is complete. Now let me trigger the source. So it should go to the home location
Okay.
first, and then again go through that.
Okay. Okay.
Sorry, what did I don't know what I search. Right, I did search, but
It's
maybe
localizing
there's
again,
some
right? It's trying to.
again. Yes, yes. Why? I think I need to keep. Mhm. Okay, let's see. Okay, it is localized now. I will just trigger the search. Now go to the search mode. Oh no, it is again triggered localized. Let me kill. Hmm. I don't know where is this weird thing coming from.
So I mean, it's okay if the robot
Yes,
goes
it, it's
to the home position to get started. I mean,
yes, it should do that. Because in the both demonstrations, so it did that because it was already in home position, so we did not actually see that the
hmm.
robot did that, but I could say that it is done. So let us once more try.
Yeah, I would like to
So
try to
yes,
check this.
yes, definitely it is in the implementation. Maybe I should have restarted the web page because it also have the status. So uh,
Try
maybe that
refreshing,
is.
or
Yeah, it has the fail counters. Yeah, let me see if this works, and if not, then we'll start fresh. Okay, localization is complete right now. Search.
yeah, now it's going
Yes, now
home.
it's going
Yeah.
in the home. Yes,
Okay.
now it's going home.
But there's something weird going on there in the the web
Yeah,
page?
because I did I did not. Let me quickly restart this. Yeah, yeah.
Okay, yeah. Now we can see properly. Yeah.
Because that is because of the web pages cache function.
Mm.
So my dog position is also gone. So because it uses the caches,
Okay.
control. It's maybe I can just
Yeah, it's
throw
fine.
this
It's
thing.
fine. Don't worry. Okay, so maybe
Yeah,
we can try one more search to see
yeah.
how it does,
Okay,
and then
yeah.
we can finish it.
Okay, so now it has. Okay, what happened? Okay, something is. So let me start quickly. Start everything fresh. So you saw that okay, it worked. It went back to the home to start the search, but maybe I did not restart the web earlier, right?
Hmm.
And so maybe that was the interference coming from. Let me kill this thing. And oh no, what did I do? There's no thing as for no. I should have done the other one. This one, I think this is the parent.
Try Control Z to release the
Control Z.
terminal.
Let me try if it is
Yeah,
still.
just open a new one.
Yeah. PS minus. I'll just see if it is not properly killed again. Okay, kill 20551.
Hmm.
Okay, now it's. So let me go to the web page and run. What was that? Python 3 HTTP server. And port is 7,000. Oh no. Python 3. Okay, I'm good. And so this thing is still. Okay, let me remove this faulty thing. So let me reconnect here if it is connect. So yes, so enable everything looks fresh, field counter 0. Yes, I think this is time for us to, let me quickly check if there is any service. Okay, localization completed, trigger completed, attach. I would also like to restart this one, just not to take chances. Everything fresh, so we don't have any error. Globalization done. Okay, so my manager is here, and let's kick in. Node started in warehouse lab, so now it is ready. So if I send the enable, so it should say okay enabled. But for that, let's go to this one and leave. Okay, so now we want to start as is, right?
Hmm.
So let's enable. Let's localize. Oh no, what are you doing? So localization complete. So
Hmm.
I will trigger this search. Yes, search is now. It'll try to go to home position again. Okay, it's already there. So now it is following the waypoint. So it is detected the card.
Hmm.
So let's see if it ends the search.
We can see it there in the web page also. appearing.
Yes. So search still is searching. It is going towards attracted towards this.
Hmm.
Okay, now it's I think it's figured out. So there is so now source is green, right? So because it is
Hmm.
found. So now we can attach. So it will go to the approach point, which is I think 70 centimeters. No, 50 centimeters away. Okay, now it has clearly
Mm.
not worked. Maybe because of the interference, it is not able to localize. But the direction was good. Uh, it thinks it is such.
Yeah, so
Okay.
I think, can you check the lap time, Kailash? Because I think it's about to
Oh yeah, about to finish. Yes, 1 minute
continue.
only.
So, okay. Okay. So, okay, then I think we can leave it here then now for the live
Okay.
demo, and we can go with some questions. So, yeah, now it's
Okay.
the moment for everybody for dropping your questions for Kailash regarding his project. So, I saw an interesting question
Yeah.
from
Okay.
Pratik that he said earlier. He said, was a state machine used for triggering the localize, search, etc.? And he also says, when should behavior tree be used? So then, in this line, my question would be, why did you decide to go for building this state machine? Did you consider ever creating behavior trees for this kind of behaviors like localized search and all that?
Oh yes, that is definitely a thing to go with. They are very robust and very flexible, right? That alongside with the node server, the lifetime nodes would be ideal things to implement this kind of state machines. But because of the complexity and the learning curve,
Mm-hmm.
so I choose to stay with the Python-based state machine that I implemented. It is simple and configurable. So it is just managing the functional calls.
Mm-hmm.
Because it gave me greater flexibility for modeling these complex behaviors and transitions. So while ROS2 lifecycle nodes are, I would say, excellent for managing the lifecycle of single node, it is very useful in the startup, cleanup, and shutdown transitions. So because of the simplicity and measure, main thing is due to the learning curve. So and learning curve along with the time complexity. So I rather stayed with the simple and manageable in the limited time for this project.
Mm-hmm.
Yeah.
Okay. Yeah, makes sense. Um, okay, then there is another question around here. So from Ricardo, he says, how do you differentiate between the legs of the shelf cart or the legs of something else like the chair, a table? And to that, because that one is very easy, I want to add. So, uh, uh, wh- how are you doing to differentiate more specifically between, for example, so the legs of the shelf and, for example, the charging station, which also has that intensity plates.
Yes. So there are a few things that so as I mentioned earlier, so I implemented that cost-based selection algorithm, I would say criteria. So first thing, so it has difference in the shape, the size, shape and size. So the dimension of the card, the spacing between the reflectors is around 60 centimeter for the legs of this card, whereas for the charging station it is much narrower. It is almost half, right?
Mm-hmm.
And and also the location. When we are doing the search and it finds the card, right? So sorry. First, I would say in order to find the car, so it detects the leg. So there are like four out of four, so there are a total of four elements nearby in this controlled environment of the warehouse lab. So there are 4 reflectors, so it could make almost like at max maybe 6 different leg combinations. So because it is so it's only 6, so I implemented like cost based leg source for all these 6 combinations. So the cost is based on the average intensity. So more near you go to the card or this any reflectors, so the reflection increases, hence the average intensity, right? And also the leg spacing is what we are looking to maximize. So um, it is 60 centimeter, so that is also added to the cost. If the leg is 30, so it will give you lower points, and if the leg is longer, so it will give you higher points. And also I have used the another filtering technique, which is if the detected legs is less than 60 sorry less than 50 to 60, then it will ignore that location as well. So this is the cost-based technique that I use to figure out whether it is charging station or the card.
Okay. Okay,
Yep.
so let's go with one last question.
Mhm.
So this is uh, because we saw your demonstration, um, uh, which was very cool, by the way. And
Thank you.
so the first loop, let's say, it went everything went very smooth, and especially in the attaching of the robot with the cart. It entered very centered. It stayed at the very center of the shelf, and everything went very smooth. For the second one went a bit worse. The robot kind of fall short in getting properly inside the shelf, and the third one also got even worse than the second one. So why these differences between the different attaching processes? Because once the legs are detected, and the cart frame and the approach frame that you created especially for the project are published, shouldn't everything be more or less similar? But in this case, we saw lots of discrepancies between the different attaching processes. So why is that?
Yeah, I think yeah. So it is because they transform maybe the frame. It is maybe I can tune the first thing I can tune the in the 3 point approach process. So the yaw, it adjusts the yaw, and then it moves to closer to the approach, and then so on, right? So maybe I can a little bit tune the threshold to be it's stricter, so that the position is we have like more precision, so that it is more precise. And also the once the TF is published, so it is live, so it does not use the static, it uses the live. So because of the robot's movement, the reflections, this data changes, right? Data changes, and so does these the TFs. They also move in the real time as robot moves, so sensor data changes, and so these TFs also little bit shake little bit. And because we need very high precision in that card, so because there is no very much of space to play with, so I think because of that moving card, so card transforms, so it was not able to precisely do in the second. And in third one, I think that it has more to do with the interference. So I can maybe my the point the cost based selection did not work properly. It maybe the interference. So I think I can implement better the costs there. So I think that is more to interference.
Mm.
Thank you, Albert.
Okay, okay. So can you show us for a moment that slides that you created that were super cool with the TFs and all that?
Oh, super cool. Thank you for
Yeah, yeah. I think
yes,
no,
this
I
one.
think they are really nice because they show in a
Yes.
Very graphical and easy way to understand how it works. So can you show a bit further where the other frame appears?
Oh, okay. Further. So here, right?
Yeah,
So
yeah. Okay. So just to summarize, basically, you think that it's mainly probably a problem of these two frames, right? Card frame and approach
and
frame.
yeah. So yes,
Mm.
because if you see in the real okay, we are already kicked out of this session. Sorry. So in the real time, what happens? What I notice is these uh, points, these are not static, so they are also moving with the data because data is changing. So these are based on the midpoints of the laser group. So laser group are changing, it is flickering, right? And because of that movement, so this whole setup of the card frame, attach frame, and this is moving, right? So wherever there is like different light intensities or the interference, so this thing have more noise, right? So that's why because and this card is very I think it has to be near perfect, so in order to smoothly run because of the dimensions. So because of this, that kind of flicker, maybe my I can improve on my cost calculation so that it can approach neatly in my future enhancements.
Mhm. Okay. All right, Kailash. So then I think we are going to leave it here. So yeah, if you want to share your camera one last time so that we can see you, and you want to say some last words, there we are. Ready.
Yeah, last words today, for maybe not for always. Thank you again for having me here, and thank you all, especially Alberto, Ricardo, Miguel, and Guris. Sorry if I didn't mention you. I know your contribution was very much helpful and paramount in my journey throughout. And yes, thank you for the construct, for giving me this opportunity to upgrade my learning and try to say I'm trying to morph into robotics software developer, and in my journey the construct helped me a lot. Thank you again for that. And to all the ROS community, I find that this ROS 2 middleware is really awesome. It makes the life of a developer easy, and I would like to just shout out to all those guys who have directly, indirectly, throughout the course of the time contributed to this project. Thank you all. Thank you me for, again,
All
for having
right,
me here.
Kailash. So let me give you an applause, and yeah. So thanks a lot. Okay, so yeah, then we can leave it here. So thanks everybody for attending, for your nice comments in YouTube, for your questions. I hope you enjoyed the presentation. I hope you've been able to learn something from what Kailash has presented to us. And yeah, hope to see you all in the next ones. We are going to, as you already know, having these ceremonies every more or less the last Friday of the month. So hope to see you in the next one. And as always, keep pushing your robotics learning. Bye bye.